Welcome back everybody. So today we will talk about Lagrange polynomial. So it means it's about finding some polynomial curve which will be passing through some given points. So here I am showing 3 points. So here is the x-axis 0, 1 and 2, and they have y values here. So the problem will be about finding curve which passes through these points. So there can be many different kind of curves, but the one found by French mathematician Lagrange is fundamental in the field, and so we will talk about it. And it's illustrative, and it's basis for many other interpolation methods that are used to find polynomials or any other curves which are fitting the data. So we have just formulated our problem. Now let's go on to see how to solve the issue. So let's go to the Wikipedia page on Lagrange polynomial. So you can see that here are the points. So the curves are, this curve is passing through the points here. The approach of Lagrange is very smart, very simple as well. So here is the general formula, you can say, but I will talk based on example. So here, if you have 3 points, here you have 3 x's and 3 y's. Yeah? So each y's are quadrat of the x's, yeah? And to find a curve which are passing through each point means when we let's say this is the polynomial that we are trying to find, and here if we put x in place, put some of the x's here, then we also put here, we should get the corresponding y values. So let's say if we put value of 1, here will be some 1 minus 2, 1 minus 3, some numbers here. So here will be like, it will be 1, this will be 1, this division. However, the other factors will always be 0. Here 1 minus 1, 0, so everything will be 0 here. Here as well. If you take an example on number 3 or x2 here, then this one will be 0, this one will be 0, so this 2 will be 0, and then this will give us 2 minus 1, and this is 1, 2 divided by 2 equal to 1, and this is 3 minus 2, 1 as well, so it will give us this. So the idea is to have multiplication of these strange factors, so that if you put a value of 1, then you will have 3 members, and if you use 1x, then the corresponding member of this sum, or 3 members, which consists of these things, the corresponding this element will be non-zero, and which will equal to 4 here. Then others will be 0. So here what elements we put is that, now let's see in the formula. So the formula is here. If it will be the Lagrange polynomial overall will be like this, from j to k, all the x's, and each lj will be equal to this one, and the y's are the values of y's. So we will multiply this l, lowercase l, by each y's, then we will sum, then we will get capital L, or the Lagrange polynomial. So each member L is the corresponding to y's are multiplication of these terms. So this is what? This is xm xm is xm, as you see here, or you can say from the multiplication that xm runs from x0 to xk. So what have to say? For each x, you will have this some member which has without any index x minus x0 here, then xj, j corresponds to lj here, and j also corresponds to yj. So every member of this pairs of x's and y's will have this multiplication, and here we will have this x's running from 0 to the last x's, and in the bottom and then in the numerator we will have xj. Xj means we will, depending on the j, we will change this j value, and here we will have general x. And so this will ensure us to have zeros in, if we insert just the x's we have, yeah, if we insert one of the x's, insert here, or this actually sum of this all items here, then all the members with this else will be 0 except 1. Though of course the one which is not 0 will be equal to 1, and it will be the L which is corresponding to xj. So if we are inserting the two resulting polynomial, if we put here x, let's say x5, then the result will be L5 will be equal to 1, then all these other items will be equal to 0, and L5 will be 1, and L5 and Y5 will be multiplied, and the resulting result will be just Y5. So this way, this is quite simple way that we just from construction we make these elements, so that if we just put x0 here, all in these things, then the first member will be equal to 1, this result here, others will be just 0 by construction, because we chose this members, so that this our x0 is here subtracted from x, here also subtracted from x, but here we don't have this member itself being subtracted from x. So that ensures that every other member will be 0. Here in the bottom we will have just these members, so that if we put here 1, then all will be equal to 1, or here if we put 2, all will be 1, so that the remaining only member, this 1, 4, 9, this will be left just as themselves. So similar example here. So the idea is this, and let's see how to interpolate or find the curve for this dots. I have here an example. So to do that, let's import this package, import numpy. We will import numpy, and from sci-fi interpolate package module we will import Lagrange method, and from matplotlib's pyplot module we will import it as plt as usual. And so it's I will just not to get confused, I will just import them, and let's define our x's. We should be given some points. So points should all have x and y coordinates, right? So here I have just the example of 3. We have 3 x's. If x1, 2, 3, no? And we will have y's, corresponding y's. So y will be just 5, 7, 50. If you plot them, the plot will be the same as the one I showed you here. So corresponding to 1, if x has value 1, y will be 5. If x equals to 1, y will be 7, and etc. So have to find the curve or Lagrange polynomial which is passing through these points. So it will be simple. We will just put this x1, x2, x3. We will be put them here and here, and y's are here. Y's will be put here, put here. So it will be a quite simple calculation. So how it's done can be done easily in Python. So there is from SciPy we imported Lagrange method. So that method will do everything for us. So if we just in input we will put our x's and y's, then we will get poly. So let's see this polynomial, this poly 1D is polynomial. So coefficients of that polynomials are this. So it will be just polynomial, which will be just something like this. 29 x plus 5. So it's just the representation of this polynomial in MATLAB's NumPy poly 1D object. So this way it has already been calculated, and so the Lagrange calculation, this has already been done automatically for us, and the coefficients of the resulting polynomial are given here. Yeah? And the one thing to mention here is that if you have 3 points, if you have 2 points, there will be just 2 points. So there will be only line which will be passing through. If you have these 2 points, there will be line. Yeah? So polynomial will have degree 1. If you have 3 points, you can have, as from here, if you have 3 points, you have multiplication of x and twice, like 2 x's are multiplied. So you will have at most 2 degrees polynomial. But if these 3 lines are on the same line, then the polynomial can become just linear. So even you have 3 points, you can have a first degree polynomial. So the maximum degree is 2 for 3 observations. So this is the theorem which proof of this will be referenced here if you ground. Okay, and so we have polynomial. So let's plot that polynomial. Now to plot that, let's create some series of x's and x's which will be spanning from x0 is here 0, x2 is here 2, and 100 elements. So our x-pole will be just 100 points between 0 and 2. And if we have poly 1D, and in that poly we will just insert our x-pole, then we will get corresponding y's. So I name it y-pole like this. And let's first plot our scatter. Then on top of that we will plot our polynomial. So polynomial, they're here 100 points we have, and that's it. So we have created a curve, polynomial curve, which is passing through these 3 points. So basically we have created some second degree or parabol for 3 points. So just to explore the results a bit, I will not talk about something new now, but we will just change the points and we will see how things are changing. Let's say we have if we have 2 points, what will happen? Let's just and if we play like this, okay, we can take it out. Actually, here must be I have only 2 points. So 2 points, and we will have a line linear function. And let's see how this code looks. So this negative slope curve, yeah? It's like this, and if we decrease our, okay, let's put this back, and let's decrease this size to 5, and let's interpolate. So our the result is just like this. Let's put here 2, so that we have. So polynomial will be not the smoothest one with 100, but it will be some curve. This. So, and that's it. And by giving any number of x's and corresponding y's, you can achieve any polynomial you want. So now I would like to talk about how behind the screen this polynomial is calculated. So we know it's calculated just as this, but how these things are calculated themselves, how this multiplication is handled in MATLAB, Python. So for that, I will show you some formula, some examples from internet, and also I will show you how it's handled in sci-fi. This sci-fi interpolate module itself. We will have a look into the codes of this module. Okay, so here I found one example on GitHub. This page where he just created the formulation of interpolation, and with some example. Here example is being done here and here, so he has some plotting function, and here Lagrange, the main function of our interest is here. Here he is just creating a P object, which is polynomial object, which is similar to our this poly object, which is the result of Lagrange here. And here he is just doing the multiplication as this. So if you remember this thing, and he's running loop here, and if I and g equal to, then skipping, continuing, right? If I and g are different, he is putting xi, xj. So this looks very similar to what we have here. So here, this x is here, this xj is, we can understand this as xm, then xi is here xj, and so he's running through all j's, all x's here, yeah, and he was also running through all i's, so all these j's here, then he's skipping if they are equal, xij are equal, so if jm cannot be equal here, these are here, and ij here cannot be equal, he says, and then he will get the multiplication of all these terms here and topmost, and then the result of this function subfunction will be topmost, and that he is multiplying topmost by yi. So basically this sum is being achieved here, this sum equal, then we will get some object, then just the multiplication is being calculated as this, and we will have these points. These points will give us x's and y's. Then from this we construct it, and this just plot function is just helping to handle this specific structured objects, and this main function is just an example. So I have this is a bit old, 7 years old ago we created it. So it's using Python 2 syntax. Here if you see, remember this should be curly brace, round bracelet. But here just Python, alt Python. So I adapted the code so that it works on new Python 3. So here I will upload it into my GitHub, so you can find the link to these files from the link below the video. So here the same formulas. However, some things are different. For example, these prints have to be changed, and here this range. In his example, it will be X range. Python. You see X range, yeah? So it's not working anymore now. So I adapted these things. So this is in our main folder, the working directory. So we can import this Lagrange as import Lagrange as let's just say Lagrange. So we have just imported it, and now let's run this Lagrange main. Lagrange. Okay, this is just okay. It's called the main. So it's giving us this 4 points and the curve itself. So here the example he is taking is this. He's taking. Well, let's talk about talking here. This was commented out in my code. So he has this x0, x1, x1, y1 here, x2, y2. They were here. They were like given like this, not like my example where I used NumPy array. So he used this example, and he used this Lagrange method here to construct this p object, and then he just used this plot function, which is here handling this specific structure of here, not NumPy array. And he is just creating the same result as me. So that's it for this example. I recommend you to try this example out and try to understand each points, especially this multiplication. Yeah, I think it would make sense. It will be easy, I hope, after my explanation. And next, let's talk about let's see how this SciPy implements the method. It should be quite simple. So Lagrange, we have SciPy here. SciPy. Then we can find SciPy's location is this. So like location is this. So we can import this change working directories to bring us to the location of SciPy very quickly. So we can just delete it. So here we have come to SciPy's directory in my computer. So where it is here. My computer's directory is users my user, Anaconda 3 libraries, site package, SciPy. Inside we have come here. Inside that there's a folder for interpolate, and so here we are importing SciPy interpolate. So let's open this. I can close it now. And what we have here since we imported the method Lagrange, so let's look for Lagrange. So here it's defined here, and yeah, you can have a look at this instructions documentation. So the code is just this, just how many 11 numbers, 11 lines of code. So this is using poly1d object. Poly1d is NumPy object, which I have an example here. Just one-dimensional polynomial object. If you provide him this coefficients, it would give you just this polynomial, and you can have this polynomial as object, then you can evaluate this object here. And here you have examples. So they are using this polynomial object. So with polynomial, zero polynomial they are giving, and then here, yeah. Then the input will be x's and y's. Here they say it's y's, y coordinates, right? Then from here they will just run loop for each j, each k. J means number of x, length of x and length of k. So for each case we will have this polynomial. So here it's very similar to what we saw in this example of this GitHub code. This GitHub code, very similar. This fraction and factor, and this 1 minus k xk is x. This means x with coefficient 1. So x minus this xk. So it's just this x minus this xk, yeah, and factor or something. Here is x j xk. Our this j just the notation is just different. So this, and they continue the multiplication as the loop goes through, and then they will have the p object as here. And what they have for v, w, they have it here. So for each w they have they are initiating pt as this w y itself, yeah, the y coordinate itself. Then on it they are adding the multiplication, multiplying these terms here by loop, and they have p. That's it. So very similar approach to Lagrange. So that was it about Lagrange polynomial. Thank you for your attention. See you next time.